Hi, everyone. My name is Allison. I'm really happy to be here with Women Who Code today. I am a big fan of the organization, and you guys have been instrumental in me when I was job hunting and just starting out. So I recently joined Pinterest as an apprentice engineer. I've actually only been there about 7 weeks now, so I'm very new, but I'm also a career changer and a recent bootcamp grad as well. So I definitely know what it's like to be in the job hunt. I was just there. So today we're going to talk about a really important topic, which is big O notation. It sounds really intimidating, I think, for a lot of other people who are maybe new to the tech, maybe coming from a very non-tech background like I was. So I've tried to sort of break it down into like easy to understand concepts and try to keep it a little fun using one of my favorite movies, Disney Pixar's Ratatouille. So what is big O notation? So when we write code, it's really important to understand how that choice of code impacts the speed and the performance of whatever program we're creating. And big O notation is a really simple way to classify how quickly the runtime of the algorithm, which can also be looked at as a number of operations, or the space increases in relation to the input of n. It's usually represented by the letter n. So it's going to look at the worst possible case scenario and assume that every possible event is touched on as the algorithm is written. So here, this is our big O complexity chart. You can see there are 7 different classifications in big O notation, and they completely range in efficiency. You can see the green ones at the bottom are amazing, they're great, and they go all the way up to absolutely terrible. Please don't ever touch these. Understanding how these different data structures and algorithms fit into this big O complexity gradient can really help you choose the right ones to use, whether at work or especially during a tech interview, because these questions really do come up quite a bit. So we're going to go ahead and get started. A couple of notes. I'm going to be referencing time complexity in my examples, but these also, the concepts also apply to space complexity as well. I'm also going to be using some JavaScript pseudocode just to sort of demonstrate examples. And as I mentioned, I'm also going to be using Disney Pixar's Ratatouille because A, I'm a huge fan, and also I really like to keep the tech things fun. I think it's easier. It was easier for me to learn that way, at least. Okay, so the first one that we have here is O of 1 constant time. This is the best possible case scenario. It is right down there in that green section. It's basically a straight line across. So let's say that you are Chef Remy and you've been asked to cook your world famous ratatouille. If you don't know what ratatouille is, it is a really delicious French vegetable stew of sorts with like zucchini and eggplant and tomato and fresh herbs, and it's delightful. So the first thing that you need to do is gather all of the ingredients and spices and herbs in order to prepare this dish. You are an amazing chef, so the kitchen is obviously your second home, and you know exactly where to find everything you need. So here we have a kitchen object, which is made up of multiple other objects of vegetables and seasonings. You can see each one has a name, maybe it has a quantity, and so on. And you won't need everything in the kitchen for this recipe. So for example, you would never put broccoli or ginger into ratatouille. So in this case, you're going to grab only the ingredients that you need. So just like this, we have an empty ingredients array, and you are directly accessing each object's name and pushing that into the ingredients array because it is an object. So each one of these operations is going to take constant time, or O of 1. And this means that the number of operations won't grow with the size of the array or the size of the kitchen object. So you could have 1,000 items in your kitchen, you could have 100 different ingredients that you're looking for. It's still going to be O of 1. Because they're objects, we have direct access to each element in order to grab what we need. So this time complexity won't change. Here we have another example. So in this function, add digits up to number n. we are doing the equivalent of adding up all of the numbers from 1 to n. So if you gave it 5, it would be like saying 1 plus 2 plus 3 plus 4 plus 5. In this case, we're going to use a quick math trick, so you don't actually have to do that. So this function is also going to have O of 1 time complexity because it's going to take the exact same number of operations, regardless if you give it 5, 10, 1,000, a billion. It's still going to take that same amount of time. Next up, we have O of n. This is called linear time. You can see this is in the yellow section. It's considered fair. So not as good as the last one, but still pretty good. So in order to start prepping the ratatouille, one of the first things you have to do is to chop all of the ingredients. So here we have our ingredients array from before, and we have a chop function that's going to iterate through every single one of those ingredients in the array and console log out that ingredient has been chopped. So how long do we think that our chop function should take to complete? Or another way to think about it is how many operations need to take place. So in this case, since there are 7 elements in the ingredients array, and this function is going to need to iterate through each and every one, we could say it takes 7 operations, or O of 7. If we added additional n ingredients, let's say we had 15 or so on, it would take 15 operations since it still needs to go through every single one of those elements. So this is what when we say O of n, that's what that means. So this is also known as linear time, and this is considered a pretty efficient solution. So if you have a solution with O of n, you're probably okay. So what do you think might happen if we added another iteration to our code? Because, obviously, in addition to chopping all of the vegetables, we also need to roast them in the oven. So here we have a make ratatouille function that we've created with both a chop and a roast function. Each of those 2 functions takes in the ingredients array and iterates through every single one of those ingredients, console logging out this ingredient has been chopped, and console logging out every one of these ingredients has been roasted. So it needs to iterate through all of the ingredients twice, within chopped and then within roast. So you could say that this function takes O of 2n time, since you're basically doing everything twice. But in this case, the time complexity of the function is still only growing in proportion to n. So we're actually going to remove any constants, which would be the number 2 in this case, and just call this O of n. So this is a really important thing to note. Even if this function had additional operations and somehow came out to something like O of 4n plus 20, we would still always shorten this to say O of n, because in big O notation, those constants and those smaller operations aren't counted. Next up, we have O of n squared, quadratic time. You can see this one is other side of the spectrum. This is really bad. It's right there in this red section there. So notorious food critic Anton Ego, he's coming to the restaurant. He hates the restaurant. He judges you and your food. So you want to give him only the very, very best. So you decide to sort through all of your chopped vegetables to find only the best pieces for his ratatouille. So in our case, we're going to pretend that every single vegetable slice has a rating from 1 to n, with n being the best slice and n being the worst. So here you can see we have a function sort by best slices, and the time complexity for this function is going to be pretty bad. This is what O(n) squared might look like. This is also known as quadratic time, and one way that you can always sort of tell is you have this nested for loop. So in this particular function, we are looking at each vegetable slice and we're comparing it to all of the other slices. And then, the next veggie slice compared to all of them, the next, and so on and so on. So it's basically the same sort of thing as saying like n times n. So if the array had 30 slices, it would be 30 times 30 operations, or 900. If we had 100 slices, that would easily take 10,000 operations. As you can imagine, runtime could grow fast, and obviously Anton Ego is waiting for his meal. So we need to find a more efficient way to sort that's going to have less impact on the runtime. Luckily, there are many algorithms that are much faster than O of n squared, such as those that are run in O of log n or O of n log n time. So we're going to look at those next, and we're just gonna, pour him another glass of wine and like hope that he stays patient. So next up, we have O of log n time. So you can see this one is here in the orange section. It's considered bad. It's not as bad as some of the others, but it's still not optimal. So let's say that our waiter received an order from a mysteriously cloaked gentleman who is clearly Chef Skinner in disguise, who says, I'll have what he's having in reference to Anton Ego. So we know that Anton Ego is seated at table number 29. So we're going to have to look up his order through his table number in order to match whatever he ordered for this mysterious gentleman. Luckily, in our case, these table numbers are always kept sorted in our array of orders, which is going to be really helpful. So since they are sorted by table numbers, as you can see here in our orders array, we are able to use binary search to cut down our search time. If you're not familiar with binary search, that's totally fine. Basically, what we're going to be doing is taking the middle order in the orders array and checking for three things. Firstly, does this table match the table number that we're looking for? If so, awesome, go ahead and return that order object. If not, is this table less than the table number we're looking for? If so, eliminate the first half of the array. If not, if the table is greater than the table number, then go ahead and eliminate the second half of the array. So basically, this happens recursively, and you keep doing this until you find the one that you are looking for. Because we're continuously eliminating half of the array with each step, we could say that the time complexity is O of log n or log time. So this refers to a very sort of mathy sounding term, logarithm, which in big O notation is basically asking the question, how many 2's do we multiply together to get n? This would actually be written as log 2n, but since we remove those constants, it's actually just written as log of n in big O notation. So if n was equal to 8, it would take 3 operations because 2 times 2 times 2 is 8. If it was 100, it would take 7 operations. And if n was 4 billion, it would only take 32, which is pretty amazing. Just as a visual, I've put in here a binary search tree. Just to give you an idea. So basically, if you were looking for an element, you wouldn't have to go through every single one of these nodes in order to find it. With binary search, you could just start at that top root node and ask yourself those same questions. Is it greater than or less than this? And with each of those questions, you could eliminate half of the array. This time complexity is super optimal. It's just above O of 1 constant time. So if you're able to get whatever your solution is into O of log n time, you should be pretty pleased. That'll be a good solution. Next, we have O of n log n, which is also known as linearithmic time. This is considered bad. This is not one that you want to avoid. I think I said log n before. I think I switched them before, but log n, great, and log n, not great. Basically the point. Okay, so O log n, n log n, logarithmic time. Do you remember how earlier we wanted to sort those chopped vegetable slices to grab the best ones for Anton Ego's meal? So the last time we used a nested for loop, which resulted in O of n squared time, which was really not very optimal. So if we wanted to cut that time down, we could use the merge sort algorithm instead. So just as we did before, we can pretend that each vegetable slice has a rating from 1 to n, with 1 being the best slice and n being the worst. So similar to binary search, merge sort is going to use a divide and conquer approach, where it's going to take an array and keep breaking it down continuously, in this case until each element becomes its own individual subarray. Then it's going to sort those subarrays in pairs recursively until the entire array is sorted and joined back together again. So kind of like broken down and then built back up again. And this approach, the time complexity is O of n log n. Just to give you another visual to sort of see what's going on here, here you'd have like an original array. You would break it down until you have just one individual element left in each of those arrays. And then in step 2, you would compare 5 and 2 and sort them, 8 and 15 and sort them, and then take those arrays and sort them together until you built it back up together. So the breakdown of the original zucchini slices array happens in O of log n time, and then building it back together through sorting requires O of n time, since each zucchini slice has to be considered, as well as O of log n time to merge them back together again. This is basically the same thing as saying n times log n, and it's also known as linear-arithmetic time. So since this sort method in time complexity is a lot better than O of n squared, we would be able to get those vegetables into the oven and onto Anton Hugo's plate much faster. So next up, we have O of 2 to the n exponential time. You can see this one is really bad. This is the second worst one. It is right there in your terrible section. You want to avoid this one for sure. So the ratatouille, it's almost ready to be served, but you feel like maybe it's missing something. So as Chef Remy, you look around, you think of maybe 3 herbs that might be a nice finishing touch to add on top. And you're considering either thyme, rosemary, and or possibly majoran. So if you think through the different combinations of herbs, that's going to yield O of 2 to the n possibilities, because the number of options grow in proportion of 2 to the n. So if you just had one herb, let's say thyme, you would have 2 options, either nothing or thyme, which is 2 to the 1. If we had 2 herbs like thyme and rosemary, you could have nothing, thyme, rosemary, or thyme and rosemary, which would be 2 to the 2 possibilities. And if you had 3 herbs, you would have 8 options, which would be 2 to the 3rd possibilities, and so on. This is called a power set, and the goal is to find all of the possible subsets of the options given. And as you can see, that can grow pretty quickly. But in our case, luckily for Anton Hugo, you instinctively know exactly what should be added, and you don't need to think about all the different combinations. You know that it's just a sprig of rosemary that's needed on top, and you're good. So in general, you should do your best to avoid O of 2 to the n or exponential run times. They can grow pretty quickly, and as I mentioned, this one is actually one of the worst complexities, and it's second only to O of n factorial, which is the one we're going to talk about now. This one is by far the worst. It is right there all the way at the end there. It's basically a straight up line right in the red that you want to avoid at all costs. So being that tonight is the grand reopening of the restaurant, the tables, as you can see, are totally packed, and our waiter, Linguini, is busy running around trying to get to each one. So obviously time is of the essence. People are hungry and waiting. So Linguini wants to calculate the best possible route between the tables so that he'll walk, or maybe in his case, skate, the minimum distance between each one. So you can imagine if he had 5 tables, in order to examine each possible route, you would actually need to do 5 times 4 times 3 times 2 times 1 permutations, which comes out to 120 in total. So as you can see in the visual here, if you had 5 tables, you might, kind of go around as a circle. Maybe you want to do a zigzag, maybe another way, but there will actually be 120 different options for just 5 tables. If you were to add just one more table, that would increase to 720 operations. If you added another one, that number goes up to 5,040. And if you somehow had 15 tables, like most restaurants do, that would come out to over 1 trillion possibilities. So as you can see, this is the absolute worst of the big O notation values, and it's known as O of n factorial or factorial time. Luckily, this one is pretty rare. Another example that you might hear this reference to is a famous problem known as like the traveling salesman. But yeah, luckily this one is pretty rare. And there you have it. So that's the culmination of our beginner's guide to big O notation, and obviously our ratatouille dish as well. Feel free to check out the original articles on medium.com. I included a lot of really helpful links in there to different resources and some more like in-depth information on some of the other topics that I touched upon, such as merge sort and logarithms and so on. So feel free to check it out. I hope that's a helpful resource for you. And that's it. Thank you so much for having me. I'm really happy to be here. Feel free to check out my other articles. They have a lot of other Disney, Pixar, or animal references, Twitter, and of course the Women Who Code Slack as well.
Thank you very much. That was great. I'm going to stop recording now.